Okay, before we looked at Fleming's left-hand rule, which involves moving charge in the vicinity of a stationary B field, and from that we get a force onto the conductor, and in this case, as we looked at last time, we see the force on the wire is into the page. Now, we're going to look at Fleming's right-hand rule. This involves the situation but the other way around. Instead of having a moving charge, what we do is we have a moving magnet. So we're going to take this magnet, which has a B field associated with it, and move it in the vicinity of a coil of wire. Note this coil of wire does not have a battery attached. We've only got an ammeter so we can measure what the current is, but there's no battery source, so there's no current initially. But what we're going to do is we're going to move the magnet into the coil of wire, and so changing the magnetic field in the vicinity of the coil. So here we had a moving charge in a stationary field, and here we have a changing field and a stationary conductor. And the charges within this conductor are stationary. So let's look at this situation in more detail. We've got our magnet with a magnetic field around it and our conductor. Now, I want you to consider first the field around this conductor. At the moment, over here, the field is not very strong due to this magnet. There is some field, I have not drawn field lines that far, but it's pretty weak near this conductor. If I were to move this magnet closer to the conductor, suddenly the conductor is experiencing a much stronger B field. So by moving the magnet around, I can change the magnetic field conditions experienced by this conductor here. And now, just as before we had moving charge experiences of force in a stationary B field, now that we've got a changing B field, all of the charges in this conductor are going to experience a force, even though they're stationary. And now we get to something called Lenz's law. And this states that all of the charges in the coil here are going to move in a direction so that they oppose the force that caused it. Now, if I'm trying to move this north pole closer to the coil, that means that each of the charges is going to move around in this coil in a direction such that we get a north pole on this end and a south pole on this end. So let's work out which way they're going to flow. Let's take the situation where I'm moving my magnet towards the coil, which means it's going to induce a north pole on this end of the conductor to repel it away. Now, which way round does that mean the current is going to flow? Well, there are various ways we can use to determine what that's going to be. The first of them is to use the right-hand screw rule again. Now, before, we had it in the context where you had a current going along the direction of the thumb, and then therefore the B field around that conductor in the direction that the fingers are curling. This time, we're going to use it in a different context. Now, the thumb is the direction of the field lines in the middle of the solenoid, and the fingers are curling around in the direction that the current is flowing. So the side closest to us, the current is going up the screen. This can help us because we know if we want to induce a north pole on this end of the solenoid, we know field lines always go away from the north pole, and so therefore the current must be curling in this way. Another way to remember it is, imagine if you look directly down the end of that solenoid, you would see the current going around in an anti-clockwise manner. And you'll see how these north and south icons are arranged. If you draw the letter N and then put an arrow on either end, you see those arrows are kind of going around in an anti-clockwise fashion. Conversely, on the other side, the south pole, if you took the solenoid and looked straight directly down that end, you would see that the current appeared to be going clockwise. And likewise, if we draw a letter S and put an arrow on each end of the letters, then you see it looks like something going around clockwise. So if you prefer that way to remember it, then that's fine, but also make sure you're comfortable using this method as well. So if I were to move the magnet this way, closer to the coil, while the magnet's moving, I would be inducing a current this way, just like we last saw, so that there is a north pole on this side and a south pole over here. So the current is flowing this way through the ammeter, so I'm going to draw a dial underneath to display what the ammeter is reading. The dial would be this way. However, if I were to try to move this magnet away again, the coil would also want to oppose that change. And so now it's going to want to try and attract this magnet back towards it. So it's trying to make this side south and this side north now in order to attract that magnet. So you can see the current's now going to be in the opposite direction, going this way through the ammeter as soon as I try to move the magnet back away. So if I move the magnet away from the coil, we get a current induced in this direction, and if I move the magnet back towards the coil, we get one in the opposite direction. So if I move the magnet backwards and forwards, I'm going to end up inducing an alternating current in my coil. And in fact, this is exactly what they do in generators. You can see now, it doesn't matter whether I move my magnet backwards and forwards or my coil backwards and forwards, they're moving relative to each other still. And in fact, in power stations, what they do is they normally coil that spins in the vicinity of a magnetic field. So in this case, our magnetic field is stationary and then the coil spins around. If you imagine it back in this context, 1 minute the north pole will be near the end of the coil, and then the next minute the south pole will be near that end of the coil. Likewise, I could instead turn the coil around, so 1 minute this end is near the south pole of the magnet, and then if I spin it around again, the next minute the other end is near the south end of the magnet, which is analogous to what's happening over here. And we can use Fleming's right-hand rule to work out which way round this coil is going to spin. We use the right-hand rule in exactly the same way as we did the left-hand rule with F, B and I, except now the force, what we really mean is the motion, so which way the coil is moving at the time. So in this example, we've got our coil spinning this way around, which means that this side of the coil is going to be moving upwards and that side is going to be moving downwards. So let's look at this right-hand side of the coil first. Our motion, our thumb should be pointed upwards because it's moving upwards. Our field is going to the right, so we would have to rotate our right hand until our forefinger was pointing right, and you'll find if you try that, that means that your second finger ends up pointing into the page. So that means, therefore, that the current is going that way, and therefore on the other side of the coil it must be going around that way. So that tells us which direction that current is going to be induced. Of course, if we decided to spin the coil the other way around, then the current will be induced in the opposite direction. Remember that you do need to use your right hand for this rule, hence the name.